happy to have Sebastian Baum, a new postdoc at Stanford. He will talk about the Paleo Detector for dark matter and supernovae.
All right. Thank you, Don, and thanks for the invitation. So I'll talk about rocks, but not the rocks, the kind of rocks we just talked about. Although now I want to talk about them. All right. So what I'm going to talk about is, we call them Paleo Detectors, but it's really what it is a mildly crazy, and I hope to convince you in the next hour or so that it's mildly crazy and not totally crazy. So a mildly crazy idea how you could look for things like dark matter or neutrinos from supernovae, really for anything that gives rise to KV scale nuclear recoils. All right. So most of this work was done before I went to Stanford. And the people, let me just point out the people we did with Andrei Trukier, who maybe some of you know as one of the people who started direct detection for dark matter in the first place, and then went away and did many other things, and is now sort of back in physics, and a fun character. Katie Fries in Stockholm and Texas now, Maciej Gorski, who's a LHC experimentalist in Poland, Pat Stengel, who's a postdoc in Stockholm, and then for the latest papers on this, we teamed up with some people in Amsterdam, so Tom Edwards, who actually just now is moving to Stockholm from Amsterdam, Rally Cavanagh in Amsterdam, and Chris Wenninger. And these are, in particular, Christoph is an expert on statistics and helped us figure out how to do a better analysis of this. All right. So let me start by telling you what is the kind of physics we want to look for. So I already said, right, what we want to look for are nuclear recoils. So one of the things that gives rise to nuclear recoils that we want to look for are WIMPs, right? So WIMPs are a good dark matter candidate. And the basic idea behind this, and this is the classic idea for the direct detection experiments, is most of the time these WIMPs, right, they just go and fly right through everything in their way, but every once in a while, these WIMPs could scatter off an ordinary atomic nucleus and give it a tiny, tiny kick, right? But that's what you want to look for. That's how we would look for WIMP, how any direct detection experiment looks for WIMP. In some way, all you want to do is you want to see if there's a nucleus that got a little kick. And of course, we know this is an extremely rare process, otherwise we would have long seen it. So just to give you an idea of how rare it is, so the Xenon one-ton experiment that has put out the data, I think I calculated this number, if I remember correctly, it's 10 billion xenon nuclei in there. Over the time scale of a year, they think not a single one of them got a kick from dark matter, right? So that's the level of rare we're talking about. And the kick is tiny, right? So here I'm plotting the energy the nucleus gets from a WIMP in a very optimistic case. So this is sort of the most energetic nuclear recoils you could get as a function of the mass of the nucleus from 1 to 200 GeV. For different WIMP masses, 5 GeV, 50 GeV, etc. So at most, in the most optimistic case, the only thing I want to take away from this is you can get something like 10 keV or so. It's a tiny amount of energy you're looking for, right? What else can we look for? So another thing that gives rise to nuclear recoils are neutrinos, right? So this is coherent scattering of neutrinos, what was just discovered, or by now it's something like 2 years ago maybe, at coherent. So right, it's just a neutrino coming, elastically scattering off the nucleus, and again, so here I'm plotting the event rate as a function of the recoil energy. All of these lines are from solar neutrinos, what they would do. This is for a xenon nucleus, but qualitatively these plots look the same for any other nucleus. So all of this is solar neutrinos. They go up to something at most, you're going to get like 1, 2 keV, something like that. Then you have supernova neutrinos, which is this line here, which gives you something that goes up to more, something like 10 keV or so. Then you have atmospheric neutrinos, right? So this is cosmic rays hitting the atmosphere, producing all sorts of particles, but also producing neutrinos, and the neutrinos coherently scattering off nuclei. And they give you somewhat harder interactions of something like some tens to keV up to 100 keV. Okay, so that's the kind of physics we want to look for. Of course, people have done that for 30 years, right, or so. And the prime experiment that people run are direct detection experiment for this, right? You want to look for KV recoils of ordinary nuclei. And I could not find a nice picture for this, but this is the first experiment that I know of. In '87, they had 750 grams of high purity germanium. And all I could find is this sketch. And we've come a very long way from this since then, right? So now the latest incarnation is the biggest current experiment is xenon 1 ton, and they're upgrading it to xenon n ton. They have 2 tons, right? And now instead of this tiny thing, you have a person standing on each of these floors. So we've come a long way. We haven't seen it yet, right? We have not seen neutrinos in these experiments because they're not big enough yet. We haven't seen dark matter. Well, probably because dark matter is not friendly enough, it doesn't scatter often enough, or because dark matter is something else. But it doesn't mean that this game is done, right? So dark matter could just be scattering a little less often than we might have hoped for, and neutrinos, we know they're there, and we just haven't built a big enough experiment to do it yet. So what do people do? Well, we're going to keep playing this game, right, and build bigger and bigger and bigger machines to do this, because in the end, all you want to do is, right, you want to have more exposure, you want to have a bigger target. But when you keep playing this game, it also becomes more expensive, right, and harder to operate this machine. So we were thinking, well, you know, is there a different way? So these are the people that are sort of sitting around in a number of rooms trying to figure this out. So this is André Drucker and Katie Fries, and this is Pat Stengel. And I wouldn't be here talking about this if we wouldn't have had some idea of how you can do this. So the basic principle between what we want to do is this. It's solid-state track detectors. And I'm showing you these pictures to convince you that what I'm talking about is not some crazy idea that is floating around. And yes, of course, we're all theoreticians that wrote these papers, and we don't know how to actually build something. But this is not some dreamland, but this is the physics we want to use is real. So these are pictures taken in the 60s, and you see these tracks here. So this is done with transmission electron microscopy. And what these tracks are damaged tracks in mica, which is a crystal, that are caused by ions traveling through the material. So in this particular case, these are fission fragments. So you have, it's mainly uranium-238, which undergoes spontaneous fission. You get 2 fragments that are sort of charged Z50 or so, that have like 100 MeV of energy. And they go some distance through this material before they stop. And while they do that, they create these tracks. You can also image them in other materials in different way. So again, this is the same material, this is floggerpite, but now it's imaged with optical microscopy after chemical etching. So people just figured this out more or less by trial and error. They figured out there are certain chemical agents you can put on a surface in this material, and it preferentially eats away these damaged features and makes them a little larger, mainly in sort of the diameter. It doesn't really make the tracks longer, but it makes them a little larger, so you can then read them out with optical microscopy. So here, this scale is 1,000 angstroms with a transmission electron microscope. Here, this scale is 50 micron, which is what you can do with optical microscopy more. But you see these tracks, again, here they are read out in a different material, gypsum, which is a salt. They've read out, so gypsum is the same stuff that you use to make a cast, right? They read out with X-ray diffraction here, again, after chemical etching. Here, the tracks are not these long things. Those are artifacts from the sample preparation. But the tracks are these holes you see here. Right? All I want you to take away from this is these tracks are real, we're talking about. It's not some crazy idea. All of these pictures are from the 60s, and you can imagine some technology has actually become better since the 60s, right? So this is a picture you can take today. This is modern high-resolution transmission electron microscopies. These were done something like 10 years ago. And what the people have done here is they've taken some prepared samples, different minerals, and they shot ions at it, and then they used this very fancy way of doing electron microscopy with modern machines to do like high-resolution detailed images of what do these tracks look like. So these are tracks going in or out of the plane, whereas this is a track going through. And so what I want you to take away is here, this bar is 2 nanometer, this is 10 nanometer. Modern technology allows us to get way, way better pictures of what this is, but also it actually allows us to see some of the details and understand what they look like. So what you can see here is, in this track, there's an inner part that is hard to see on the screen, but essentially here you see the regular crystal lattice, right? And this inner part is what people think what happens is the material melts, and when it refreezes in some materials, like this crystal, when you melt a material and refreezes, it doesn't refreeze in the regular crystal phase, but it refreezes in a amorphic structure, right? And this is what you see here. So you get these amorphic cores. Around this core here, you see a zone that also looks different from the regular crystal, but you still see a lot of sort of regular structure in there. Well, how people interpret that is it's mechanical stress in the material, right? So you still have sort of a lattice, but it's deformed in all sorts of ways. Here in mica instead, mica is not amorphous when it refreezes, so here all of this is interpreted as chemical stress in the material.
So this must have to do with, so is there some understanding of why it would be amorphous?
Yes. So why the material is amorphous when it refreezes?
It must be a time scale thing. And
well, so crystallography is a big field in itself, and I'm not an expert at all in it. All I know is there are materials, when you melt them, they refreeze in amorphous phase or in crystals. I'm sure that people understand why this happens. But yeah, crystallography is very complicated, right? So let me instead try to tell you a little more about these tracks. So one problem with these tracks is we don't understand really from first principles there's no like unified theoretical framework to define when do these tracks form, how do they look, etc. Different aspects are understood. I'm going to show you some ideas of how these tracks form, but there's no unified framework that really allows you to do this. Luckily, we can go in the lab, right? And we can make these tracks by shooting ions into the target we want, and we can read it out and check, right, how do the tracks look. So you can go and calibrate, you can understand it. So it's not the end of the world that there's no unified theoretical framework for this. So let me tell you about the models, how people think these tracks come to be. So one model is called the thermal spike model. And here the idea is that you have an ion traveling through your crystal lattice. It interacts with the electron cloud in your lattice, in your crystal. And essentially what it does, right, so it's a charged object, there's Coulomb interactions, it just starts shaking the electrons around. Then the electrons start shaking their neighbor electrons around, which they call delta electrons. And you just literally build up motion in your electrons, right, which is thermal energy, right, it's just temperature. So what you do is you heat up the material and it melts. And then when it refreezes, maybe you get this amorphous cores, right? There's another model called the ion explosion spike model. So you see all of these models have very nice names. And the ion explosion spike model, here the idea is you have the ion going through your lattice. Again, it interacts with the electron clouds. But now the idea is it sort of pushes all of the electrons away from where it went through. And then you have the ions in the lattice sitting around, right? Because now they suddenly become ions, the electrons are gone, and realize, oh well, we're all ions, that's not a good situation. There's Coulomb force, and we have to repel each other and go away from each other. Okay, so, and this is an idea of how you can maybe understood this mechanical stress part of the track of how it's forming. One criterion you can also get from, in particular from this picture, is that materials, in order to form tracks, so first of all they have to be sort of regular, right? So crystals are very good candidates to form these tracks if you want to mess up the structure. But what you get from this idea is one criterion to be a track detector is that you are an insulator, or at least a very poor semiconductor. The problem is if you have high electric conductivity, right? If this happens, maybe all your nuclei the ions go away a little from each other, but they immediately just bounce back and settle back in a nice state, right? So if you want to form some sort of permanent damage in your material, you better be a conductor. So what's the use behind all of this? So the idea that we came up with is, well, okay, you can use these solid-state track detectors. A lot of natural minerals actually would form these tracks, or are observed to form these tracks when ions go through them. And the key part about these tracks is that once you make them, they stick around. It depends on the particular properties of your material, how long they stick around. Very roughly, high melting temperature, high melting point materials are good for retaining tracks longer. It depends at the temperature you keep your material at, etc. But there are many materials where even at temperatures of a few hundred degrees Celsius, these tracks can stay around for timescales that are like 1 billion years. At room temperature, I think, so the best example I know is diamond, where at room temperature, these tracks stay around for something like 10 to the 60 years. So these tracks, once you make them, they can stay around for a really, really long time. And nature is nice. It's given us really old minerals, right? So Earth is like 4.5 billion years old. It took some time for Earth to settle down and become nice and cool and quiet, and minerals to sit in nice and quiet environments. So the oldest minerals on Earth are order a billion years old. I think the oldest single one is like something like 2.5 billion years old. But yeah, so there's plenty of materials on Earth, plenty of minerals that have formed a billion years ago and sit in nice quiet environments. And modern technology now allows us also to read out these damage tracks in those materials with high precision. So what does this allow you to do? Well, that's the idea, right? So we have something that's sitting around and that's measuring nuclear recoils and recording that information for a billion years, right? And what that buys you is a ginormous exposure. So instead of building an ever bigger detector, you have a small detector that sits around and records everything, all the nuclear recoils in it for a billion years. So if you would think about, maybe you can read out 100 grams of material. I'm going to show you how we think you could actually recover these tracks. Say you can read out 100 grams of material that has been recording stuff for a billion years. If you want to match that with a normal direct detection type experiment, you can maybe run for 10 years if you're optimistic. Because your grad students don't want to wait for 10 years before they can write a thesis about this. So okay, let's be optimistic. 10 years, you would have to build a 10 kiloton detector. And I don't think anybody's dreaming about building a 10 kiloton xenon detector, right? And the other piece is that the nanotechnology allows you to read out tracks with a spatial resolution that basically gives you, and I'm going to show you how it works, that gives you a energy threshold that is roughly sort of keV scale for nuclear recoils. So that's, if you think about it more broadly, what can this detector do? What you could search for this is you have a kiloton year or 10, 100 kiloton year sort of scale detector that has keV thresholds for nuclear recoils. So if you compare this to what we have today, right, the keV sort of scale nuclear recoil energy threshold detectors are something like the big liquid noble gas detectors, and they are sort of in the ballpark of a few ton years, right? Whereas what we have that has an exposure comparable to this, 10 kiloton years or so, or 100 kiloton years, that's like Kamiokande, right? Super K or Hyper K are sort of roughly around this ballpark. But they have much higher thresholds. But it also tells you what kind of physics you could not go after, right? So if you have something that has much higher energy depositions than this, then you're not going to win. So for example, if you think about very highly energetic neutrinos, what we do with IceCube, the energy threshold of IceCube is gigantic compared to this, but also their exposure is much larger to this, right? So if you think about something like this detector is not going to be useful. But if you think about something that's low energy and has large exposures, exposures sort of in a kiloton year, then this is a way how we think you can get exposures that are much larger than anything we can build today.
So what's keeping that 100 grams so small?
It's the way you do the readout of this technology. Okay, let me just throw in, we're not the first people to think about this. So back in the 90s, people have run this kind of experiment. They used mica, and they've set a limit on, so they looked in mica, which is a crystal that occurs in nature, they looked in old mica for tracks that come from dark matter, and they set a limit, so this is the usual WIMP plane, right? WIMP mass, WIMP cross-section. The limit goes down to something like 10 to the minus 31 square centimeter, so compared to anything we can do today, it's not very impressive. All I want to say is, right, this has been done before. The reason they couldn't do it better back then is basically technology. There are some quirks we've also worked out that we think you can do better now, or that maybe our idea is better, but the main reason they could not get better than this is exposure, that they could only look at a tiny effective target mass. Okay. So let me tell you the one piece, if you think about how you want to calculate your signal or how your backgrounds looks in a detector like this, that's different than what you would do for any other type of detector, like a normal direct detection type experiment. So the difference is, instead of measuring the recoil energy through the scintillation light or whatever you want to do in your particular detector, now we're going to measure these tracks, right? And so what you want to know is, right, you already know your recoil energy spectrum, because that you calculate the same way as you would do for any other experiment. The new piece is now you want to turn your recoil energy spectrum into a track length spectrum, right? And the only piece you need to know for this is the stopping power of your ion of a given energy in your material. And then you integrate that stopping power to give you the total track length, right? Now the loss of energy of these material of ions in material of these energies of a few keV, tens of keV, 100 keV is mainly due to electronic stopping and nuclear stopping. And the nice piece is you don't have to care what it comes from. You just count everything together. And the reason you don't have to care about is that both of these pieces have been shown to give rise to these tracks, right? So you don't have to discern. You just calculate the total track length. And so here I'm showing you the track length from 0.1 nanometers to something like 10,000 nanometers for recoil energies of this is 10 eV up to 1 mega eV. In epsomite, which is a particular example of a salt, these curves look very similar in many other materials. So one thing you can read, so these are the different constituents of epsomite. So one thing you can see is the lighter your nuclei gets, the longer the track gets you get for a respective recoil energy. Now, the thing that is much longer than anything else is hydrogen. Turns out, though, hydrogen tracks, so it's a proton, right, a hydrogen atom. A proton going through a material typically does not make a track you can read out. So we're not going to take into account the tracks that you can get from protons, but you're only going to get tracks from heavier Z ions. We've looked at what happens if you can see these tracks or not, and in the end you have to go in the lab and calibrate do you see these tracks, right? But for the rest of the talk we're going to assume protons don't make tracks. Only atoms that are heavier than alpha particles, so heavier than helium ions, or have larger charge make tracks. So it's only for this material, the only thing that matters then is oxygen, magnesium, and sulfur. And you see the track lengths from these are relatively similar. For each particular mineral you have a one-to-one relation of a recoil energy and a track length. But in reality you're not going to be able to, once you see a track, to say what it actually came from out of this. So you're just going to be able to see, look, I measure a track of say 100 nanometers. Okay, it's going to correspond to a recoil of, in this case, something like 25 keV or so, right? And there is some width in this. But you get a good idea of what is the recoil energy, right? Which now allows you to imagine, so imagine you measure a bunch of tracks, right? Now this is, what you're going to gain by this is energy resolution of your signal, right? Whereas in a direct detection experiment, you count how many photons do you get, and that gives you the energy resolution, for example. Here you count the tracks and it allows you to energy resolution. The second piece you can read out from this track is also sort of what is from this plot, is what are the thresholds you're going to be able to achieve. So we put some benchmarks on here. So imagine you have, I'm going to tell you later how this works, this is some form of Xray microscopy where we think you should be able to get a spatial resolution of your tracks of something like 50 nanometers, which roughly tells you, right, the shortest tracks you're going to be able to read out are like 50 nanometers long. And so now you just go and follow your line and you end down, okay, so this corresponds to recoil energies of a few keV, 3-4 keV in this material, but it's order 1 change to go to any other material. And that is a recoil threshold that's comparable to what you can do in a liquid xenon type experiment, right? So you build if you're able to do this, you have the same energy resolution threshold to what xenon experiments have. Now, imagine you have a much more higher spatial resolution readout. And the example we put on here is Helium Ion Beam microscopy, which is a fancy version of just general ion beam microscopy. And this has spatial resolutions on a nanometer scale. It's been actually demonstrated to have sub-nanometer spatial resolution. But if you think about a lattice in a crystal, the typical distance between the atoms is on the order of a nanometer. So you can't really talk about a track that's shorter than, a few lattice spaces at least, right? So let's say we can do a nanometer. Then the energy threshold that responds to is a few tenths of eV, right? So now if you could do that, that's something that's comparable to what you can do with cryogenic bolometer experiments to look for nuclear recoils. All right.
Sorry, before we on, I think you explained it, but why you don't care about the Z line, the H line?
So basically, this is a very rough argument. It's not how it actually works. People have understood it since, but the very rough argument, and qualitatively it holds, is you just have to. There is a threshold to the stopping power you need in order to deposit enough energy locally, right, to create a lasting track. And the lower your charge is, or it's the charge to mass ratio that matters in the end, but the lower your charge is, the lower your energy deposition is going to be. So this is why hydrogen doesn't give you a lasting track normally. So you just don't deposit enough energy. One nice thing that also comes out of this is if you calculate the stopping power, if you have electrons going through your lattice or gamma rays going through your lattice, they do not deposit enough energy. If you have muons going through, right? They're not sufficiently ionizing to give you a lasting track. And if you think about a direct detection experiment, what that buys you is you have perfect sort of rejection of electronic recoils, right? Which is great, because if you run a liquid xenon experiment or any other direct detection experiment, you spend a lot of your time on just getting rid of electronic recoils.
So I guess I would have thought that what mattered was the charge of the ion, right? But these heavier ions, they're still mostly singly charged, aren't they?
No. They get stripped.
They get completely stripped,
Yes.
so they're highly charged.
Yes.
So that makes sense. So that makes sense to me, right? So it's the large charge that's stripping
Yes.
off a lot of local
Right.
electrons, and then that's what's causing damage to the
Yes.
material. Right? Yeah.
Yeah, so if you think about, so what you need to know really to calculate is, right, you need the charge, if it's electronic nucleus, you need the charge basically, and you need to know the gamma factor or something of it, right? Which is why electrons of that energy wouldn't matter, because they would be relativistic and they don't deposit enough energy. Okay? So what I've told you about is, I just said, right, we just take the stopping point and integrate that, right? Now you could wonder, how do these tracks look, right? So this is Pat and me going to different beaches in California. If the tracks would actually look like his hair, everything I just told you would be entirely useless, right? Because then just the range is not a good proxy for how the track would actually look. Luckily, the tracks don't look like my hair, but if you look at how tracks look in experiments that have been done, and there's simulators for how these tracks would look like, they look like my hair, which means most of the time it's very straight. You can get unlucky and you can get something like this, okay? You can get a kink in your track, but it's rare and you get one of them. You don't get a track that looks all curled up like this, right? So what we're going to use in our calculations is just the range. In principle, you're going to go in the lab once you would do an actual experiment and calibrate this, right? But the range is a good proxy. Now, of course, dark matter or neutrinos are not the only thing that could make tracks, right? So I have to talk about backgrounds. That's sort of boring, but if I don't talk about backgrounds, you're never going to believe me that
I was waiting for, so not boring.
right, that it's only mildly crazy and not totally crazy. So let's start with natural defects, right? So what we want to do is we want to take a rock that nature has formed 1 billion years ago or so, and look if there are any tracks in there, right? So what we did, what we win by this is this enormous exposure, right? What we have to pay for is we're not running a controlled laboratory experiment anymore, right? But we're just picking up something that nature has made. So one thing you would ask is, right, does nature make things that look like these tracks? Now, crystallography is very complicated and I have no idea about it, except what people tell me when we ask them. What they tell us is, no, nature doesn't do this. What nature does when it grows crystal, it forms single-site defects, so there's one atom missing in the lattice, or there are line defects that stretch across the whole monocrystalline domain. So nature, and the answer was not no, the kind of defects you want to look for, what dark matter or neutrinos could do, like 10 or 100 nanometer or so long tracks. This was something very, very rare if a mineral forms, but no, we understand how they form, and this doesn't happen. This is the only thing that nature does.
Do they say that because they haven't found any? Because, of course, the problem is you're looking for something very rare.
Yes.
So there better be a better argument than we haven't found anything.
They say that
right?
because they claim they understand how these things form, and these kind of defects just wouldn't form from the theoretical understanding of how crystals form. But, of course, as you say, it's something one should try and check in the lab, right? And one can prepare samples that wouldn't have been exposed to for example, dark matter or any other sort of or any form of background for 1 billion years that are relatively young, right? And you could check, right, do these natural defects, are they in there or not?
So it seems like maybe a natural defect would look different in detail than this heated thing.
That you could also hope for.
And so at least as a
Yes.
few test cases.
Right. So you could go, right, you can try to do these things in the lab and see how well you could discern them. Right. I agree. There might be some also like the details of track. Now the problem is typically in the way I'm going to show you how we're going to read out a track. We're going to be able to sort of resolve the length of the track, but not sort of how the track looks in its shape. Because then you would have to have these tracks, the diameters of the tracks are a few nanometers, so you need a readout that has this resolution, and it's very expensive. And you can only look at so much material with that. But yes, in principle, there might be ways to do this. But what we're going to do...
At least to check the question mark is
Yes.
sort of
Yeah, I agree. So what we're going to do is we're going to say, look, natural defects are not a problem. Because everything we know about them is they just don't look like what the signal we want to go for would look like. So what about cosmic rays, right? There's cosmic rays coming, and they rain down on your sample, and they do make damage, right? Either you have a charged cosmic ray just going right through your target, and that's really bad. That makes, of course, that looks just like you want to look for, except it's typically much more energetic. Or, except charged cosmic rays, you also have, well, you have muons, which are charged, but not we talk about when we talk about charged cosmic rays. You have muons coming, right, and they make neutrons by interacting with stuff in the vicinity of your target. And then neutrons come, and neutrons are not your friends if you're on an experiment like this, because the way neutrons lose energy in material is by elastically scattering of atomic nuclei. So they do exactly what dark matter would do, right? Now, how do you get around this? We do the same, or we would do the same thing that any normal direct detection experiment would do, right? You just put a lot of material between you and the atmosphere. So you go deep underground. Now, if you run a normal direct detection experiment, right, you have to build a ton-scale experiment, and you have to go there, and you have to drive a truck there, and somebody has to stand next to the machine and see that it works. Now, we don't need to do that, right? We just want to get a piece of mineral, a piece of rock from somewhere. And we're talking about a small piece of rock. So you can do that from much, much deeper in the Earth. So what I'm showing you here is the number, it's the neutron flux that you get from cosmogenic muons, which is the only thing that's left when you go to large depth. All the charged cosmic rays get stuck in the Earth very quickly. As for different depths, so this is the depth in rock in kilometers, and a neutron flux that is appropriate in units for the kind of experiment we want to run, so it's per square centimeter per gigayear. If you go to a depth of 2 kilometers, which is where the deepest labs we have now to do direct detection are, you're going to get something like 1 million neutrons per square centimeter per gigayear. But if you would go to a depth of something like 5 or 6 kilometers or so, the flux is much slower, and we're now talking about seeing 100 or 10 neutrons or so going through the material. And that's a number that we can handle. Yeah, give me a second. Because, so if you think about, you shouldn't think about this the way you think about a normal direct detection experiment. If you run a normal direct detection experiment, what you're trying to do is you're trying to have a background-free signal region, and you count a few number of events in your signal region. What's going to happen here is in sort of at the discovery threshold that we're going to claim, you're going to see a lot of background events and a lot of signal events. There's going to be thousands or tens of thousands of signal events. So if you get 100 neutrons going through, that's a background we can live with. Okay, so the way the analysis works is much more like you think about a collider type experiment than about a direct detection type experiment.
So I just wanted to understand, why are neutrons such a big problem for you? Do they really create tracks?
The neutron itself does not create a track. Neutrons itself essentially just go through, right?
I see,
but they scatter elastically off nuclei, right? They do exactly the same thing that dark matter or neutrinos, etc. would do. That's why there's such a big problem in any type of direct detection experiment. Now, something you do in a normal direct detection experiment to get around neutrons is, so they scatter, and a typical mean-free path is a few centimeters. So if you have a big experiment like xenon, your neutron is going to scatter multiple times typically in your target volume. So that's something that's nice if you run a normal direct detection experiment. It's something that helps you to somewhat bring down that background. Now we can't do that, right? Because we're going to see these tracks, and these tracks don't come with a timestamp. We don't have time resolution, right? So in that sense, neutrons are a little worse for us than they are for direct detection type experiment. It's a sort of order one making it worse, like this.
There still must be something you can do with that clustering. even though
Yes,
it's
but it's centimeter distances. You would have to tie them.
a big enough sample.
Well, they're too far apart essentially. There's too many other tracks.
Oh, okay.
Or each neutron can have multiple backgrounds as a
Yeah.
Yeah, right.
So yeah, what we do is I'm going to show you how we deal with the neutrons in a little, but we take into account everything that one neutron would do, which is like, depending on the material, it can easily be 1,000 interactions. Okay, let me just...
Don't you have to know that the rock was at that depth for 1 billion years? Rocks
Yes.
go up and down and
Yes.
move around.
So again, this is something I know nothing about. So we go and we talk with geologists who study the Earth and study how stuff moves around in the Earth, and they know these things. And they tell us that, so you can understand how stuff has lived, how certain regions in the Earth, how they've been evolving over geological timescales, over these timescales. And yes, as you say, you have to know how long it's been sitting down. So let me give you one example. So one kind of mineral we're going to be interested in, we're going to see in a second why, are what's called marine evaporites, which are minerals that form at the bottom of evaporating oceans. And they slowly get buried in the Earth. Now the problem is that, so today they can sit down at depth of 10 kilometers. So they slowly get buried down in the Earth. But the problem is that burial speed is essentially linear. Well, the burial speed is constant, so the overburden is linear in time. But the flux, the background you're going to get from cosmic rays is exponentially suppressed with the depth. So what that tells you is, well, you don't win, right? If I bury with linear speed, even if I spend a relatively short period of my time at shallow depth, I'm going to be swamped with backgrounds. But it turns out that these salt deposits are actually a little more interesting than that. So what happens is these things get subducted, they slowly get buried in the Earth, and they sink down to depth of somewhere between 5 and 10 kilometers. And then you have other material piling on top and just keep exerting pressure on that. So one thing that happens is, because they're at such a depth, actually they get hot, and the mineral sort of undergoes recrystallization, which removes all of these damaged tracks. It sort of gets cleaned up by itself from temperature. And then you have that material pushing down on it from the top, and then what happens is you form what are called salt domes, or salt dampers. You have salt essentially shooting up to shallower depth, and then sitting there for hundreds of millions of years. So there's a nice story of how you can get a sample that originated from the surface, but it went down, it then got rid of all the background tracks being made in there earlier, and being brought back up to a location that is sort of shallower, which is good because you don't want it to actually sit at 10 kilometers because it's too hot down there. And if your material is too hot, you get rid of the damaged tracks as well. So, and geologists understand this. And the story I just told you about the salt divers, this is not like the one, it's not a fairy tale of this happens if you're really lucky, but this is a very, very typical process in salt deposits. Okay? So one idea, just to tell you how you would actually get these rocks from down there, is you use boreholes. Right? So when people drill boreholes, and these are geologists or people looking for oil that drill these boreholes, you pull out cores from these, bore cores, that are sort of like 1 meter in length and have a diameter like this roughly. So each of these boreholes has much more material than a few kilograms, right? So there is a source of material from deep down, and just here I've shown you to get an idea of how deep down. These are the deepest boreholes that I know of in the on Earth. There's a number of boreholes, many, many more than what I'm showing you here, that are like 5 or 6 kilometers deep or so. So most of you know about the space race, I assume. There's also been a borehole race that most people don't know about. This one, the Soviet Union won. So they made it down to 12 kilometers. The US only made it to 10 kilometers. Okay, so this is the deepest borehole in the world. But there are plenty of boreholes that are sort of 5, 6, 7 kilometers. And as you can see, they're not all in like one place on Earth, but you can go and you can get these rocks from different places on Earth, right? We're not talking about, we don't want to build a custom borehole to get our rocks. It's very expensive, and maybe at some point in the future we want to do this, but what we're talking about is getting samples from existing boreholes, because people pull up these cores and they pull up much more material than they ever need. Alright, so what do we do to deal with cosmogenics? We do the same thing that any normal direct detection experiment does. We go deep underground. Okay, and the next background, of course, is radioactivity. right? Which is, again, something you run into if you run a direct detection experiment. There's all sorts of radioactive processes, alpha decays, beta decays, spontaneous fission making neutrons, and all of this stuff gives you a lot of background and gives you things that look like what dark matter and neutrinos could do. Now, the first thing you do to get around this is, of course, you pick a sample or you build your material, your detector from stuff that is clean, right? That's radio pure. So in our case, this means, right, we have to get material that doesn't have an awful lot of radioactive elements in there. The most radioactive element, most dangerous radioactive element for us is going to be uranium-238. So if you pick up a typical mineral that's formed in the crust of the Earth, so some examples are quartz or feldspar, those are the most common examples, it's typically going to have a concentration of something like 1 in a million of its nuclei are going to be uranium-238. And if that's the case, that's actually going to give you a background that you won't be able to handle. It's going to swamp you and it's going to remove all sensitivity to the kind of physics you want to look for. So we need something that's much cleaner. Luckily, Earth is nice and has provided sources of material that are much, much cleaner than the crust. So one example is the mantle of the Earth, right? So the layer between the core and the crust. Which happens to be much, much cleaner from things like uranium, but also thorium, etc. And one way how you can get them to be somewhat closer to the surface, of course, is, right, you can have something like a volcano, or like imagine like an underground volcano locally transporting up some lava that then crystallizes and forms these minerals. And some of the very common examples are olivine, something less common is schwanningite. So olivine is the black stuff you see in granite also, for example. No, sorry, it's green-ish, but you see this in granite deposits also. And the typical concentration, or the sort of on the cleaner side of what people have measured in these materials, these are called ultra-basic rocks. Stuff that's formed from the mantle is something like 0.1 parts per billion. Okay, so it's like 4 orders of magnitude cleaner than something formed from the Earth. So this is one of the benchmark concentrations we're going to use for these kind of rocks. Another source of clean materials are these marine evaporites I just told you about. The reason why they're so clean is, now here the reason was that the Earth mantle is just clean. Here the reason is that seawater is one of the cleanest things we have on Earth. So when you crystallize material from an ocean, it's going to be very clean. Now this number that we're going to use here, some of the examples are gypsum that I already talked about, or halite, which is the salt you eat every day. It's just a weird name for it. We believe these can be an order of magnitude cleaner, roughly, than stuff that's formed from the mantle. Now this number has not actually been measured. It's something we extrapolate from what people have measured, and what we understand about the ocean, how minerals form. The reason this number hasn't been measured, while this number for the stuff from the mantle has been measured, is that geologists care about this number. Because they want to know both what is the typical concentration of uranium and stuff like this in the mantle of the Earth, but also what is the cleanest rocks. And that's because radioactive processes are what is the heat source of the Earth. So if you want to understand how the Earth works, you have to understand the heat that's being generated. Whereas nobody really cares about what are the cleanest, as far as we know. There's no geological application of what are the cleanest minerals you can get from the sea. And it's you can imagine if you want to measure a concentration that low, where only, 0.01 parts per billion of the elements are uranium, it's hard, right? It's hard to do this, expensive to do this. So we are currently running a campaign to trying to measure these numbers. But we're just going to use this benchmark. And we think it's reasonable, but I just want to warn you, it's not actually measured. So let me quickly tell you about what's the most dangerous source of backgrounds you get from radioactivity. It's neutrons for us. And the reason is, we already talked about this, right? Neutrons lose their energy in exactly the same way that they do exactly the same thing as what we want to look for our signal is going to do. They elastically scatter off nuclei. So there are 2 sources of neutrons we're going to take into account when we're going to model this background. The neutrons that come from spontaneous fission. So for example, you have a uranium atom that goes into these 2 fragments. Now these 2 fragments, these are like Z50 or so fragments of 100 MeV. They make these tracks that I showed you about earlier. These tracks are long, they're big, they're easy to find. These tracks are not a problem. They are orders of magnitude bigger than anything you would want to look for. So you can get rid of these tracks. These are not the problem. The problem is you also produce a few MeV neutrons. Another source of neutrons is what's called alpha N reactions. So there's a lot of alpha decays going on in your sample. Again, the tracks from the alphas, even if you could recover the tracks, which is not clear at all, this is the same story I told you about with the protons. If the alphas themselves would make tracks, they would be like 10 microns long or so. So those tracks, again, are much, much longer than what you care about. But every once in a while, you're going to be unhappy, and your alpha particle is going to hit a nucleus and undergo a hard reaction, and it's going to kick out a neutron from that nucleus. So these are the source of neutrons, and you calculate what you're going to get from there. You calculate the neutron spectrum, and then you calculate all the interactions you're going to get and all the recoils you get. And then we can look at what is the background you're going to get from this. And I just want to show you one piece of this, which is two minerals that are otherwise quite similar. This is halite, which is rock salt, and this is gypsum, which are chemically quite similar, except that gypsum has hydrogen. And what you're going to see here, these are the same scales I use. So this is the recoil spectrum as a function of, so this is the recoil energy. And you see that in gypsum, we assume the same number of the same concentration of uranium there. You see in gypsum, it's a few orders of magnitude lower. Right? So what we do is we take into account all the interactions that elastically scatters and scatters and scatters the neutron, how much does it go down. So the reason why this happens is that you have hydrogen in there. So imagine if you have your neutron going through there and it hits a normal nucleus. The normal and it undergoes elastic scattering. The normal nuclei are much, much heavier than your neutrons, right? So you have this ping pong ball hitting the bowling ball, and the ping pong ball is actually not going to lose a lot of energy, but it's going to fly around for a long time and keep hitting more bowling balls and kicking them around a little bit. But you're going to have a lot of interactions. Whereas if you have some hydrogen in your target, you have other ping pong balls, right? Because a proton is just as heavy as a neutron. So it's a good neutron moderator, which is what brings down this background. So this tells you about something about what kind of nuclei do you want to use. You want to have nuclei that are clean from uranium in the first place, and preferentially have a little bit of hydrogen, because the hydrogen helps you to massively reduce the number of background events you get from neutrons.
I just wanted to know, could you use these bigger tracks to just measure, for example, the uranium content of your sample? So eventually you do a sample, you get a sample, you essentially can measure your background just by looking at all those. Yeah.
Exactly. Yes. So this is one way how you could measure the uranium concentration. You could also do mass spec, of course, or there's a number of techniques that people use to measure uranium concentration. You could just count the fission tracks, which is a little indirect, because what you need to know for the number of fission tracks to make use of that is you need to know the age of your sample and the uranium concentration. So you can use them in two ways. Either you already know the uranium concentration, then you can know them to learn about the age of your sample, which is interesting, or you can play it the other way around, right? But certainly the fission tracks are useful to do a number of things. So yeah, and this is what we're going to essentially assume when we do sensitivity forecasts. We're going to assume we know the normalization of these backgrounds within some reasonable accuracy, right? And we're going to just use that in our background modeling and then calculate what's our signal to noise ratio we get from that. Right? Okay, so that's what I'm going to say about radioactivity. Now the next piece, of course, if you look for dark matter, a background is neutrinos, right? And I don't have much to say about neutrinos. They can be your background or they can be your signal. There's nothing you can do. There's nothing you can do against neutrinos, right? You can't shield against them. They elastically scatter, and all you can do is, well, you just have to live with that background, or you can use it as a signal, right? But so you just go and calculate it. So what does the background look like? Background budget look like? So here I'm showing you epsomite just as an example. So it's this funny type of material. It's a salt. So we're going to assume it has this uranium concentration of 0.01 parts per billion that I showed you about earlier. And here I'm showing you the track length spectrum as a function of the track length, right? So this is from 1 nanometer up to 1,000 nanometer. So this line here, this orange line, is the neutrino background. So all of these pieces up here, all these wiggles, these are solar neutrinos. Then somewhere down here, there's a few supernova neutrinos. And then there's atmospheric neutrinos down here. And you can't really do anything about this background, right? It is whatever it is. The other piece you have here, this blue line, is what you're going to get from radioactivity. In particular, this is what you get from the radiogenic neutrons, right? So this line, of course, now this is going to scale up and down with however much uranium is actually in your sample, right? So this line, you can, in some essence, in some aspect, you can actually do something about this line by picking a cleaner sample. So the second piece you can read off from this plot now is, except just looking at these things, but okay, so we're going to have two sort of regimes of background, right? If you're going to look for tracks that are somewhere over here, of length of like 10 nanometers or so, your dominant background is going to be neutrinos, right? If this is your sample where the neutron background is that high. Of course, if you have a much dirtier sample, it's still going to be neutrons. But let's assume that if we have these nice clear samples, your dominant background is going to be neutrinos. Whereas if you look for longer tracks, if this is where you have your best signal-to-noise ratio, something like 100 nanometers or so, your dominant background is going to be radioactivity, right? And we're going to come back to this, why this is important. So now let's think about how does this look compared to your signal. So if you want to look for dark matter, here I'm showing you two spectra from WIMPs, elastically scattering off your target. This is a 5 GeV WIMP and this is a 500 GeV WIMP. Don't worry about the normalization. Normalization is just proportional to the cross-section that the WIMPs interact with, right? So just care about the shape. So if you want to look for a sort of GeV scale WIMP, you're going to see that, right, your best signal-to-noise ratio is going to be somewhere in this region, right? You want to be able to see sort of 10 nanometer or so long tracks. Your dominant background is going to be neutrinos. Okay? If you look for heavier dark matter, if you look for something, honestly, these look very similar once you go above something like 15 or 20 GeV or so. If you look for something like above that, some heavier WIMP, you want to look at longer tracks, right? Your best signal-to-noise ratio is going to be somewhere here, 100 nanometers or so. So you don't need as good spatial resolution you want, but now your dominant background, you're going to be limited not by the neutrinos anymore, but by the neutrons, right? If you want to look for neutrinos instead, so here I picked supernova neutrinos as an example. This is going to be the signal you look. Again, these are the neutrinos and these are the neutrons. Your best signal-to-noise ratio, again, is going to be at something like 100 nanometers or so, right? And what's going to limit you are the radioactive backgrounds. How could you, before we get to what you could actually do with this in terms of the reach, how could you actually do this readout? So one idea that we've been thinking about is Xray microscopy, but it's a sort of fancy version of Xray microscopy. The main reason why you need to do something fancy is you want to get good spatial resolution, right? So you can already guess, the shorter my wavelength is, right, the higher energetic my X-ray beams are, the better my spatial resolution is going to be. So what you want to do is you want to go to a synchrotron, which is a good source of hard X-rays, high quality beams, and you want to do something called small angle X-ray scattering. So what you do is you take a X-ray beam from a synchrotron, you focus it on your sample, you take a diffraction image, then you scan it over your sample, and you piece together all of these diffraction images. And then you do the same thing you do in a hospital. If you get a CT, you rotate your sample a little bit, you play the game over again, and what that allows you to do is to get a 3D readout of your material, right? You can take a bulk sample and get a 3-dimensional readout of the structure of the material. This has been demonstrated, so this is just a show-off picture these people have produced. They took a glass colloid in there just to show off what is the spatial resolution you can do. This has been done in Switzerland at PSI. They've demonstrated 16 nanometer 3D resolution in your bulk sample. The downside, of course, is you need to go and you need to have a synchrotron light source for this. Now, you see, of course, I'm not showing you a picture of a track, right? The reason for that is that this has not been done for tracks. Tracks have been reconstructed with small angle X-ray scattering, but not at these resolutions. So this is, we think in principle there's nothing that goes against this, and when we talk with people that do this, they also sound optimistic. But just as a note of caution, so we're proposing to do a particularly challenging application of this form of X-ray microscopy, but we think it can be done. And then the other question, of course, is, right, so we're going to assume this is the resolution you can do, something like 15 nanometers in 3D. But what is the sample size you can process? So we think in a reasonable time frame of a few months or something like that, you could process roughly like 100 gram of materials. So that's going to be our benchmark for this. We think you can do something like 15 nanometer spatial resolution of 100 grams. You wouldn't take a 100 gram sample, you would do a series of smaller samples.
These domains are what? Are they
So what you actually measure,
This
so
material?
this is glass colloid, this is glass, so this is material and no material. But what you really measure is electron density with Xray microscopy. So let me tell you about one other way we think you can do the readout. So this is this Helium Ion Beam microscopy I was telling you about earlier. So it's something that's been developed very recently, but now you can go and you can buy one of these machines. And they're not very expensive, they're like a few $100,000 or so. And what you do essentially is you shoot a low energy ion beam at your target, low energy helium ion, and you measure backscattered helium ions or electrons being emitted from the surface. And what that allows you to do is to achieve nanometer scale resolution, right? So this is a graphite flake they built, and they've only taken this picture to demonstrate how well does this helium ion beam microscopy work. They've demonstrated 0.3 nanometer resolution of this edge of the flake. But you can do something fancier. Here they looked at a rodent kidney. So this bar here is 5 microns, and this is 50 nanometers. So I like this picture because what it shows you that you can actually zoom this technology, right? You can decide how big is my sample I want to look at, and what's the resolution I need. The better my resolution is, the smaller the sample I'm going to be able to look at also is, or it's just going to take you forever to look at it. But it's a zoomable technology, which is very nice, and it can achieve very high resolution. Again, you see I don't show you tracks, right? So this hasn't been demonstrated for tracks, although we believe we don't see any reason why, and people we talk to don't see any reason of why this couldn't be done for tracks. So there is one additional complication, right? So what you're doing is you shoot a low energy ion beam at your target and you look for backscattered stuff. So you're not going to be able to read out a bulk sample with this in this way, but you're only going to be able to see some surface of it. And it can read out something to like 100 nanometers deep or so. What you would do then is, the idea we have for this is you take this helium ion beam and you read out your surface to a depth of something like 100 nanometers. And then this machine comes with other ion beams, higher Z ion beams, and you can take these higher Z ion beams to mill away the surface you've just read out. And you can do this in a very nice controlled way so that you don't damage the next surface. Now that's very slow, so what you would actually do is you strap a pulsed laser to this, and the pulsed laser can get rid of most of the surface much quicker. It also heats it up a little bit, so the last layer you would have to do with this higher Z ion beam. But that's sort of the rough idea. You can use a technology like this. You can do something very similar with electron microscopy. You read this out layer by layer. So effectively in the end you're going to get a 3D picture of your sample, and the resolutions you can achieve are sort of on the scale of nanometers. It's the best resolution that makes any sense for this, because if it's even shorter than that, there's no point of calling it a track anymore. However, the price you have to pay for this resolution, of course, is you can only process a much smaller sample. So we think you can do something like 10 milligrams with this in a time frame of a few months. So what can you do for this for dark matter? So let me show you some sensitivity projection. Just to remind you, this is the curve I showed you earlier. This was our 5 GeV guy and a 500 GeV guy. Right? Now, if you want to look for the 5 GeV guy, you want to look here, right, at a few nanometers. So what you want to do is you want to have this helium ion beam microscopy technology I showed you about, right? Whereas if you look for heavier WIMPs, now you want to do the Xray microscopy thing, right? Because you don't need the track length resolution to be that good, but you see you don't get as many events here as you get for the lighter WIMPs. So you want a bigger sample. So this is what the reach looks like when we calculate it. So this is the sort of the high resolution, the helium ion beam readout idea, 1 nanometer resolution and an exposure of 10 milligrams times a billion years. So here in gray, it's probably very hard to see in this slide, but this gray curve and shaded area, those are current limits from direct detection experiment. Here, just to orient you, is the xenon neutrino floor. Now the neutrino floor, it looks different for each target and each experiment you run. So this is just for orientation, what it would look like in a normal xenon experiment. And all these colored lines are different target minerals that we calculated. So you see the reach is orders of magnitude better than anything one can do today, right? So the experiments today sit somewhere up here. So this technology should allow to improve the sensitivity by orders of magnitude. You also see the differences between the individual samples the different minerals are relatively small. And the reason for that is that what limits you here is the neutrino background. And the neutrino backgrounds are a little bit different depending on what your chemical composition of your target is, but they're not vastly different, which is why everything sort of ends up by a factor of a few to each other, right? It also tells you this is essentially the neutrino floor for our experiment, right? The reason the neutrino floor is quite a bit higher than it is for xenon is if you think about a normal direct detection experiment, right? What you're going to measure at the neutrino floor is how well can I characterize the flux of neutrinos or the number of events I get from neutrinos today. Whereas we don't have time resolution, we're looking at a 1 billion year old sample. So what gives us the uncertainty here on the number of events you get from neutrinos is, well, over the time scale integrated over 1 billion years, how many neutrinos came from other sources, right? So we put a much, much larger uncertainty. We say we put 100% systematic uncertainty on a normalization of the neutrino flux in here when we make these predictions. So if you want to look for heavier dark matter, right, you want to use the Xray microscopy readout. So 50 nanometer spatial resolution, 100 grams, we're going to say, times a billion years. And again, these are the current limits. And now you see the colored lines, which are sensitivity predictions. They differ a lot between different elements, right? Different minerals. So the best minerals, epsomite, which is an example, basically what you want is a marine evaporite that has some some hydrogen. You can be a factor of 10 to 100 or so better than current limits with the way we've done the sensitivity predictions here. The reason why the differences are so large is that halite and epsomite, so these two lines are example of marine evaporites, whereas olivine and nickel bischofite are examples of ultrabasic rocks. And we assume that marine evaporites have less uranium in there than ultrabasic rocks. And remember, the dominant background here now is radioactivity. It's the neutrons, right? So the cleaner, the better, which is why they win. And the second reason why these pairs of lines then are very different is the presence of hydrogen, what I showed you above, reducing the background you get from neutrons by orders of magnitude. So there, it does matter to some extent what kind of target you have. If you want to beat current limits, the best way to do it is to have a very clean material, like these marine evaporites, that has some hydrogen in there. Now, luckily, if I would put on a bunch of lines of other marine evaporites, or minerals where I assume the same uranium concentration, that have hydrogen, they would look very similar to this line. You get an order 1 spread, so you're not relying on picking out this exact type of mineral, right? But it's classes of minerals that matter to give you the sensitivity predictions. So let me quickly talk about what you could do for neutrinos before I end. Can I have a few more minutes, or do people need to run?
People need to run, we'll run.
All right. So neutrinos you can search for in exactly the same way, right? Elastic scattering. We haven't seen a lot of astrophysical objects in neutrinos. This is a short list, and it misses one thing. Of course, we have seen the Earth in neutrinos. But one of the things that we have seen in neutrinos are core-collapsed supernovae that are close by, right? So to give you an idea of what the signal would look like, now if you talk about a normal direct detection experiment, you're either going to see, people talk either about seeing the burst of neutrinos from one individual supernova that's close by, and the rate of supernovae in our galaxy is something like 1 in 30 years, or they talk about seeing the neutrinos collected from all the supernovae in our universe, except those in our galaxy, because they only happen once every 30 years. So all the neutrinos from all the supernovae in the universe, this is what's called a diffuse supernova background. So here I'm showing you the spectrum. This is the diffuse supernova background. Now we're going to run an experiment, right, that integrates over times that are hundreds of millions of years or a billion years. It's much, much longer than the 30 years or so, which are the rate of core-collapsed supernova explosions, or people think that's the rate of core-collapsed supernova explosions in our galaxy. So we're going to average over that, right? For us, it's going to look like just some number of events, and we don't know where it came from. So this is the flux you're going to get from supernova in our galaxy, and you can see it's roughly a factor 100 or so larger than the flux you're going to get from diffuse supernova. You also see that it's a little harder, it's a little more energetic. The reason for that is that the diffuse supernova flux is redshifted, right? Whereas the supernova in our galaxy, they all sit at redshift 0, so that's why the flux is a little harder. Okay, so again, this is how the spectrum looks. Now here I'm showing you the background spectra, and the white is the signal spectrum. So you want to look for something like 100 nanometer tracks. The reason why this plot looks different than the plots I showed you before is that what we've done here is we've taken into account the spatial resolution in this plot by essentially just smearing all the tracks with how well can you reconstruct this. So what can you do? Here I'm showing you what is the smallest supernova rate in our galaxy you can reconstruct as a function of the uranium concentration in different targets. So let's focus on epsomite, which is again going to be our best sample. Now, I said, right, we think it's like 1 in 30 years or so, but nobody's ever actually measured that number in any direct way. So here I put on 2 predictions of what this number could be, which is like 2 per century or 3 per century, roughly, which is what people think. So if you cross this line, we think you have a good chance, or these lines you have a good chance of measuring it, right? So the bottom line is, if you have a Paleo detector that has less than 0.01 parts per billion in uranium, which we think again is reasonable for marine evaporites, this should allow you to measure the local galactic supernova rate. Now that's already, I think that's pretty cool. Nobody's ever done that. And it's a number that's important for galaxy formation, for example, because the supernova rate is directly proportional to the star formation rate, and star formation is very important to understand how galaxies form. But we think you can do something much, much cooler than this. So if you again go back and think a little bit about the big picture, right? Normally we run an experiment and we measure what's happening now in the lab. Or we run a telescope and we look out into the universe and we measure what happened on our light cone, right? Now you have an experiment that carries information about stuff that happened a billion years ago. There's very, very few examples of how we can run an experiment that measures things that are not on our light cone. So one of the things that allows you to do is, now imagine, right, so of course in each individual sample, although it carries information about what happened a billion years ago, it doesn't come with a timestamp, right? So it's not very useful. But you can imagine, let's take a number of these samples, right? A number of different rocks, where one of them is like 100 million years old, the next one is 200 million years old, etc., right? Now, in each of them, I'm only going to be able to measure the integrated rate, but now I can take a numerical derivative and I can actually measure the time dependence of the rate, right? I can really learn something about physics that happened a long time ago. And the example we picked here is to say, look, the supernova rate in our galaxy most likely is not going to be constant in time. This number I showed you earlier is what's the time average supernova rate, right? But can we learn something about the time evolution of the supernova rate, which would be learning something about the star formation history of the Milky Way? And here, just as a very simple example of how you could calculate the sensitivity, what we've done is, okay, let's say our null assumption is the supernova rate is constant in time. How well could we tell that apart or reject that hypothesis if actually the supernova rate was not constant in time? If we take a series of 10 samples, 100 million years, 200 million years, etc., up to a billion years, and we've taken 2 benchmarks of how this time evolution could look like. One is we said, okay, we've measured the cosmological star formation rate, right? We go back on our light cone and we measure how many supernovas explode there, going back in time. And you can just turn that z dependence into time dependence, say, okay, the Milky Way is going to follow that time evolution. Then you're going to get these blue dots as a function of different uranium concentration, which basically tell you, well, you can't tell these things apart. The reason for that is, if you go a billion years ago, in this model of the cosmological star formation rate that people have measured, supernovae a billion years ago exploded like 1.5 times as often as they do today. So it's a very small shift, which is why it's so hard to tell apart. There's a different model that's been built from Gaia data, where people think they've found evidence for some starbursts. So you just count stars and count the metallicity. You can guess when they formed. It's a complicated thing to do, and there's many people that argue about how reliable it is. But let's just take this serious and say what they measured is how the Milky Way evolved. In their model, a billion years ago, the cosmological supernova rate was 2.5 times of what it is today. And now we can say, okay, if that's the case, if it follows their time evolution, then how well could we tell this apart from a constant time evolution? And so here, this is the discrimination significance. How well could you reject the null hypothesis? And say maybe your benchmark is 3 sigma. You could do this if you have these 10 samples that are a little cleaner than 0.01 parts per billion by a factor of, I don't know, 0.7 or so, right? So this is just an idea of what could you do with this information? What are the sort of the scales of the time evolution of any kind of signal that you could pick out with this?
But wouldn't that signal be drowned out by the fact that our solar system is sometimes in much higher and much lower concentration regions of the galaxy or stars?
Right. So
Would that swamp this out?
right. So if you think about timescales, you're absolutely right. So it takes the solar system around about 250 million years to go around the galaxy. So if you talk about 1 billion years, that's a long time on going around the galaxy, right? Yes. So what this is going to tell you is the number of neutrinos that you locally get, right? Now, because those timescales are actually so long that we're going to integrate over 100 million years, you actually sample for long enough that you're not going to be dominated by sort of local effects typically, but you're going to be dominated by the supernova that happen in the galactic center, or close to the galactic center, where most of the supernovae go off. But yes, there is a uncertainty that we actually did not carefully put in this calculation, but there's some uncertainty going off from the very local contribution. So something we did actually look at is a different game you can play. So on average, right, you're going to be dominated by a supernovae going off roughly at the galactic center. But what happens if you have one supernova going off very close to you? Could you figure that out with a similar analysis, right? You could. However, the supernova, for a rather similar, simple analysis we've done, you could do something fancier, which I'm happy to talk about. But the simplest analysis will tell you something that the supernova had to go off within something like 10 parsecs from us, which is very close. Coincidentally, that's sort of the distance that people talk about where a supernova going off at 10 parsecs, or not much further than that, could actually affect life on Earth. So people have done all sorts of speculations about sort of mass extinction events being related to supernova going off. So I don't know how interesting you find these speculations, but it's certainly something that's sort of fun to think about. Could we maybe link these things together and identify, hey, there was a supernova and there was a mass extinction event roughly at the same time. There's actually a connection. All right. I think I'm just going to leave you with these conclusions, and we're rather going to take some questions. So basically, what I want to convince you of, right? We have a target, a way of measuring things. I think that basically what it is, it's a kiloton year or 10 or 100 kiloton year experiment exposure that has sort of keV scale thresholds for nuclear recoils. And what we've thought about is, right, what could you do for it with dark matter? What could you do for it for neutrinos from supernovae? But I'm sure there are many other things that, if this whole thing actually works, and of course that remains to be seen, and we have to do some experiments to demonstrate it. But I think there's many options one could think about of what are the kind of physics you could go after with this. And one of the things that I lately found more and more exciting is this idea of you could actually gain information about processes that do not happen in our light cone, but happened 1 billion years ago close to us. Thank you.
So, as I mentioned, I appreciate the background slide. Whenever I have grad students, I always say, like, spend 99% of your time understanding background, and then doing signal will be easy in 1% of your time. So, and what's nice here is it looks like you actually do have, I think I saw at least 3 sort of handles, right? You could look at the track length distribution and show that you can reproduce that. You could show a correlation with the overall background level with what you measure for the radioactive level. And then I guess even you have things that were close to the surface that the geologists tell you and things that weren't, and you could see, so you could in principle check all of those things and make sure that you actually understand the backgrounds. Do you have people working on that already, or what's the sort of experimental end of this operation?
So all of these things are very good, yes, and so these are the things that allow you to actually, if you would see something, to build trust, then it's not crazy, right? Or to build a better background model. The theoretical status so far is basically 0. we're all theoreticians, and we're talking more and more with experimentalists and pushing them to do it, and there is interest, and it's just it takes time though. What we're doing right now is measuring uranium concentrations in minerals, which is an important proxy to just tell you, right, what is possible in terms of radioactive backgrounds. Now, the next step, what we want to do is a little simpler than what you've been talking about, is just go in a lab and with the kind of readouts you want to use, show that you can actually recover these tracks. Which we think it should be possible, and from what we read it should be possible, when people tell us it should be possible. But most of the research of actually seeing these tracks in these pictures I showed you earlier are from much more energetic ions. So we have to go and show that you can actually see these tracks. Once we know how to do that, and that it actually works, then one step is to, for example, look for calibrate radiogenic neutrons, radiogenic backgrounds, because it's relatively easy to do in a lab, right? You can just put a radioactive source next to it, or you can take a sample that has a lot of uranium or whatever you want to look for in it, and you do the calibration and see, you understand the background, right? And then you can go further, right, and you can play games. Once you sort of, graduate to do a more and more proper experiment, you can start to play games and look at samples from underground, you look at samples from different depths, etc. But that's going to take time. So I think the first step, so we're currently doing just the radio surveys. The next thing is hopefully maybe this year, but otherwise early next year. We've been talking with people in Michigan quite a lot, which have an electron microscopy lab, an excellent electron microscopy lab, to do some of these initial studies, just showing that these tracks exist, and then hopefully, within a year or something, to actually start to do something for radiogenic backgrounds. But to run the proper experiment, it's going to take a few years at least.
Has there been any consideration of studying material such as a meteorite that might have has the potential of having spent time in a part of space that would have a much higher concentration of dark matter?
Yes, so people have asked me this before. We haven't done any calculations. It sounds like a very cool idea. I think the limitations of why we haven't thought more about it, the main limitations are backgrounds. So cosmic rays are a huge problem, right? If you're just sitting on a rock that flies through space and goes close to stars, and you don't have an atmosphere, and you don't have magnetic fields that shield you, blah, blah, blah. The background story is what mostly kept us from thinking more about it. But it might be worth it, and there are scenarios where, as you point out, for example, if they would have flown through a denser dark matter region, etc., where it's useful. This, on the other hand, this is also something that's quite fun for the paleo detectors to think about. It's again something we've mentioned, but we haven't properly calculated. If you integrate over a billion years, I said earlier it takes 250 million years to go around the galaxy. You're not longer sensitive to the, if you think about dark matter, to the dark matter density, the local dark matter density in the sense that we normally talk about it, but you're going to integrate over the dark matter density going around the galaxy a few times, right? So even if this detector has been sitting on Earth, it might have gone through, if there is a lot of dark matter substructure, which we don't really know too much about, there's all sorts of models for that. You could have potentially flown through parts where there is much more dark matter. You could have gone through streams, etc. So it's something we haven't properly worked out what the implications would actually be, but whereas for a normal direct detection experiment, most of the time it's a bad thing if there's a lot of substructure in dark matter, unless we happen to just sit in the overdense region, which typically we don't. For something like paleo detectors, it's not clear at all that it's bad, but it might actually be a good situation to have a lot of substructure if you can fly through it.
Perhaps these are coming, this would come from cores?
Bore cores, yeah.
Borehole cores. Are they large single crystals inside there? Is it?
Absolutely, can form quite large.
Yeah, okay.
So I've been lying a little bit about how the backgrounds work. So we've done when we do these calculations, we've done an oversimplified picture. The problem are the neutrons. So the neutrons, they scatter every few centimeters, and depending on what your target is built out of, they can go over meter scales. So what you care about for the neutron backgrounds in particular, is really the uranium concentration in like a cubic meter size volume around your target. So you don't necessarily need your crystal to be that large, but you need to know your material in that volume. And you need that volume to be relatively clean from uranium. So what we've done is, in our calculations, we've assumed we have one infinitely large crystal, because then you don't actually have to know something about the local environment, right? When you run an actual experiment, of course you would want to know the local environment, and you have to calculate the neutron background accordingly. But this doesn't have to be bad necessarily. For example, right, I told this story about having hydrogen or not having hydrogen. You don't actually need the hydrogen in your target. You need the hydrogen in this cubic meter size volume, right? You can absorb the neutrons. You don't have to absorb the neutrons in your target, but you can absorb them close to it. So again, it's not a story that's necessarily bad. It can go both ways. But this is the proper way how you want to do the backgrounds if you actually want to.
Have you thought of maybe trying to make tracks in crystals with an ion beam?
Yes. So so this is part of sort of the feasibility studies. One would look for, want to show that we can demonstrate these tracks, reconstruct these tracks. One thing you would do is, right, you could just take natural minerals and do it. But you could also, yes, you take the mineral, you shoot ions in it, low energy ions, high energy ions, you put radioactive sources next to it or neutron sources.
You make your own ultra pure
Exactly.
and then
Exactly. You do all of these things, and this is one of the nice features. Most of the background sources, in particular the radioactive background sources, and what the signal is going to look like, you can go and calibrate it in a lab and understand it, right? So although there is no first principle description of these tracks, you can go and you can do calibrations in the lab. The thing that's hard to do is neutrinos, right? Because it's hard to get a neutrino source with the right spectra and a lot of flux.
again though, all they do is cause a coherent
Right.
elastic recoil.
Right.
So you just shoot a beam from the outside with that energy.
That's right, exactly. Yeah. You can do the ion calibration. The only thing you can't do is you can sort of calibrate it by injecting neutrinos and creating your fake signal directly, right? Which would be a little nicer. But yes, as you say, you can do almost what you would ideally want to do.
Yeah, it's hard to get very low energy neutrinos in high quantities.
Right.
So, any more questions? Let's speak again.